first of all, thank you to Greg for making this meeting possible. Greg's one of my big supporters on Patreon. And so I was really happy to, host this meeting. I'll tell you a little bit about my views on physics, and I'll try to make this talk only 20 minutes so that we have tons of time left at the end to just field your questions and to talk about really whatever interests you guys in physics. So I'll start by saying that in my view, physics is stuck. Now, it's not stuck in the way that a lot of people, you might hear a lot of people already talking about. You've probably heard about the recent failing of string theory, or at least it has fallen out of favor among physicists. You may have heard about the contradictions between general relativity and quantum mechanics, how those two theories make certain important calculations which come out to completely different numbers. You may have heard that the theories are fundamentally incompatible on a certain level. These are not the ways that I think physics are stuck. Rather, I think what's gone on is that physics has actually been, the problems with physics are not recent. They've been around for about 100 years, and they've been developing for longer than that. And what these problems really are is twofold. First, that physicists have lost sight of the fundamentals about what the purpose of physics actually is. And number two, we've lost sight of the proper methods to pursue physics. The proper methods of science, the proper scientific methods for actually making conclusions about the physical world. So in the past, for a long time, if you study the history of physics, you find ever since the Enlightenment, you find a very linear progression. Physicists move from one level to the next, or well, I'm moving my hand in an upward way. Really what I should be doing is moving my hand in a downward way. When it comes to identifying physical fundamentals, physicists continued this linear progression deeper and deeper into the fundamental nature of things. So first, Newton and Galileo and Kepler, they observed the macroscopic world. They found laws about how or what I should say is they found out the nature of matter in motion. They figured out that matter always moves in a certain way. If you have a certain amount of force, that will cause a certain amount of acceleration. And then according to equations that Galileo came up with, that means that it will simply move in a certain way. From there, people started, chemists, which were kind of considered physicists at the time. Chemists understood reaction ratios between different chemical elements. They understood that if you add a certain amount of hydrogen and a certain amount of oxygen, that will always come out to some particular amount of water. And they understood other reactions as well, and generalizing over all of these reactions, they came to an atomic theory of matter. And so you can see that's a level deeper. We understand that the reason the chemicals combine in this way is because they're made of atoms that combine into molecules in a certain way. And what's very interesting about this is they were able to conclude that atoms and molecules existed far before they ever could see them. Real quick question for the audience. Guess what year people finally saw atoms and molecules? Just guess the year. Take a guess.
I'm going to guess about 15 years ago.
15 years ago? So 2010, 2009. That's a very good guess. It was in fact 2001. So obviously I kind of set it up. You can tell by the context of how I set it up, it was quite late. The atomic theory of matter was in fact proven somewhere around 1850, maybe even a little earlier. Somehow they were able to know this, friggin' 160 plus years before it was ever directly observed. Okay, continuing this linear progression. It wasn't long until they figured out that atoms were made of protons, neutrons, and electrons. And these parts of the atoms were held together with electromagnetic forces. And they could use these knowledge of these electromagnetic forces to identify how the atom was actually put together. I'd have to go over the history, but basically by studying the light that was emitted from atoms, they were actually able to figure out the way that electrons related to the nucleus of an atom. And that allowed us to make inferences, that allowed scientists to make inferences about the structure of the atom. And of course, understanding this inner structure of the atom is what gave us nuclear power. Okay? Now, each of these levels, each of these progressions gave us more power over nature. The fundamental power of science is the identification of cause and effect relationships. Once you understand a cause, you can then initiate an effect. So, for example, once you understand the inner nature of heat, you know that heat is just motion. You now know that anything that causes motion at a microscopic level will cause heat. Further, you know that any kind of heat can also cause motion, and that's the kind of thing that led to exact calculations for the steam engine. So each of these levels, once we identify deeper and deeper cause and effect relationships, each of these levels gives us more power over nature. And that is the true purpose of science, to give us more power and ability to harness nature's forces. And and think about that point as we progress, because it's going to be important. Thinking about where the true power of science actually comes from. Now, my case today is that we're no longer making that kind of progress. And that we've been making progress of a sort. It's not that physics is utterly stagnant, but it is stagnant in this particular way, that we have not made fundamental progress towards deeper understanding of deeper physical causes. Progress in that regard has not happened for at least 70 years. Now, why not? Why haven't we been making this kind of progress? Well, I think there's basically 4 causes that I want to go over, and all of these are fundamental. They're on the philosophical level, really. It's a matter of not just science, but it's a matter of what proper science looks like, what the proper goal and method of science is, as I said at the beginning. Now, first, the first problem is that physicists are no longer trying to find underlying natures. Think of it as they're no longer trying to figure out, if they were testing with chemicals and mixing chemicals together and finding out how much oxygen and how much hydrogen it takes to make water, they're no longer interested in, well, why is it that these ratios keep coming up for all of these different reactions? They're no longer interested in finding the underlying nature of things. They think the current attitude is that the purpose of science is to simply account for appearances. It's to model the phenomena. You'll hear a common phrase amongst modern scientists. They'll say, all models are wrong, some are useful. It's a very common. Who's heard that phrase before? All models are wrong, some are useful. Okay, well, so if you're, we have kind of a lay audience, but if you're around academics in physics, you will hear that bandied around about once a month, and this is indicative of the kind of attitude. So let's think about what that means. A model, in their mind, is a understanding of what is physically going on in a certain situation. So an example would be the heliocentric model versus the geocentric model. That would be an example of models, 2 different models. So what are these? These are accounts of what's really going on. When we look up at the night sky, we see planets moving through the sky over the course of many months, changing positions with respect to the other stars at the time they thought of planets as stars. We can see them changing. That's what we see. We just see a bunch of dots moving, really. But what's the underlying cause for that? Well, there's 2 underlying models. There was a geocentric model, which basically, and you might be wondering, like, wait, there was a geocentric model? Yeah, there actually was, where the Earth is at the center and Mars goes around the Earth, like the planets go around the Earth. The only trouble is they had to make Mars and the other planets do like a loop-de-loop pattern around the Earth, like almost a spiraling pattern, because that's the only way they could get a geocentric theory to fit the observations. So they actually had a model. Now, of course, there's another model that the sun is at the center and the planets are moving around it, the Earth being an object that actually moves. And now imagine what would have happened if Copernicus and Kepler, these brave individuals who questioned the status quo, at peril to their own lives, incidentally, who questioned the status quo at peril to their own lives, what if they had had the attitude, oh, well, every model is wrong, some are useful? Do you think they would have risked their own lives for a model that's just a little more useful? No, they were seeking the truth. They were trying to find the actual underlying nature of things. And how does this look like in the modern day? What is it that I would... There's a lot of examples I can give, but one of the main examples that I would cite as indicating the abandonment of underlying causes would be the abandonment of the ether. Who's heard of the ether? So to specifically, I'll talk about what I take to be the ether, just in case there's any, just so you know what I mean, because it might mean different things in different people's vernacular. So my common way of explaining this is if you suck the air out of a jar, and you have a bell inside the jar. Once the air is out of the jar, you can't hear it anymore. Why? Well, because there's no air, and so the sound cannot transfer through the jar into your ears, right? But here's something kind of cool to think about. You can still see the bell, right? And light's a wave. So that means waves are still propagating from the bell through the jar into your eyeball, even though there's nothing in the jar, or there's apparently nothing in the jar. You suck the air out, so there's apparently nothing in it, but these waves are crossing through the jar. So what that means is there's still something left in the jar. There's still something left in the jar that's waving, that constitutes, that is carrying those light waves. And whatever this something is, it must be in the vacuum, or the apparent vacuum, of space. There must be this stuff everywhere which is able to carry light. And the ether was abandoned by physicists about 100 years ago now. People stopped thinking about the ether. And it was specifically because of experiments such as the Michelson-Morley experiment, which you can make a note to yourself to talk about that in the question period. But the Michelson-Morley experiment did not, in fact, disprove the ether. And we can talk about that, but this was a disaster for finding underlying causes in physics, because the ether, because in physics we are now aware of all kinds of waves that propagate through space. We're aware of gravitational waves. We're aware of waves of light, of course. And what we found in quantum phenomena is that when we zoom in, when we look at the inner nature of matter, we find that it too has a wave-type property. What are these waves waves of? Is the question that would have been obvious to Enlightenment scientists, to scientists like Copernicus and Kepler who are trying to find underlying causes. Physicists like Newton who were able to discover the underlying cause of planetary motion. What was the underlying cause of planetary motion? It's that the sun is pulling the planets in, causing them to go in a circle. He found that underlying cause. What's the underlying cause of these waves? Well, something must be waving. What's the nature of this stuff, whatever it is? These questions are no longer asked. So, as this first point of what's really taking modern physics off track, it's that physicists have lost sight of the fundamental goal of science, which is to find underlying natures. And one way of describing that mistake is this attitude that all models are wrong, all explanations, they don't really matter, you can never really prove them. Just they're useful. They're useful mental images to help us reproduce the observations. And in my view, that's the death of deeper science. Science that seeks underlying causes. Second, in physics, we are now saddled, another problem that has caused this stagnation. In physics, we're saddled with a lot of philosophically flawed theories. I'll brush through this briefly, and I'm very open to questions on this. General relativity is philosophically flawed because it is a subjectivist theory. So here's what I mean, is it talks about the observations of a given observer. It does not describe what is actually going on. It is agnostic about what is actually going on. I mean, again, it doesn't seek to find underlying natures. Instead, what we're given in general relativity and special relativity is an account of how the events will appear to different observers. Okay, now, in physics, it's actually important to give accounts of why different observers see different things or observe different things. So, for example, there's a common illusion where, let's say both of us are looking at a fish inside of water. Because light bends when it goes from water into the air, if you and I, if I'm tall and you're short, you and I will have different guesses, we'll have different estimates of how deep underwater the fish is. And the reason for this is basically, long story short, it's because light bends when it goes from water into air. And so we will observe, if you will, the fish to be at different depths. Now, in the modern day, we have a theory that completely accounts for this difference of observation. It does not, but it doesn't simply tell us that we're going to observe different things and then, mathematically account for those differences in observation. It tells us why we observe different things. It tells us the physical cause of that difference. Namely, it's because the light is bending. Now, in general relativity, we do not have an account of why different observers observe things differently. Now, to put this briefly, one reasonable hypothesis is that motion through the ether and gravitational forces cause deformations in measurement instruments. It causes rulers to get shorter, and it causes clocks to tick slower. And as a result of these changes, people using rulers and clocks to make observations are going to make observations that are different because of these deformations caused by the ether, these deformations and these slowing of clocks caused by the ether. Now, I'm not saying that we know that that's the cause, but this is what it would look like to actually understand the cause. Instead, what we're given with general relativity is an agnosticism at best, an agnosticism with respect to causes. Doesn't really matter what the cause is. We're just supposed to write down the equations that describe the differences between the different observers. So that's the second flaw in physics, the second thing that got us into this problem, which is that we have philosophically flawed theories. There are also flaws with quantum mechanics, the other major pillar of our physical theories, but I don't have time to get into that right now. You can ask me in the question period what I think the flaws with quantum mechanics are. Now, thirdly, we are confused about the nature of the abstractions that we're using. Physics has now gotten to a point where the concepts are so abstract that fully connecting them to observation, continuing to hold them in a truly scientific way, in a way that is based on observation, not just free, whimsy of the human mind, it's starting to become harder and harder to do that. And we are not meeting that challenge in the modern day. And I could give a lot of examples, but I'm just going to give one, and that's fields. We've heard of gravitational fields, electric fields, magnetic fields. People will talk about these fields without talking about the entity that causes them. They will be confused about the nature of fields and what they actually mean. So what they'll say is they'll say, another example, they'll say, in quantum mechanics, they'll say, the vacuum contains fields. Well, if you're serious about what a vacuum means nothing. You're telling me that nothing is doing a thing. Well, if it's doing a thing, it's not nothing. It's something. Now, it's the ether. The thing carrying these fields is the ether. We know that. I can give arguments for that later if you want. But whatever you want to call it, nothing cannot be the cause of fields. And we have to get clear on what fields actually mean. We have to understand what it is. And I think there's a distinction between the fields, which are just mathematical abstractions which capture action. So, for example, a gravitational field tells you how much gravitational pull will exist at a certain location. That's separate, that field, that abstraction telling you about the action. That abstraction is separate from whatever it is the ether is doing at that location to cause that action. We don't know what the ether is doing at that location to cause the action, but that's exactly where we need to turn our scientific eye, our scientific inference towards finding out. So the third problem is being unclear on abstractions. Okay? Now, the fourth problem is that the fourth thing that has led to the stagnation is that in the modern day, all physicists stand atop an enormous, unthinkable skyscraper of prior ideas. To summarize the skyscraper briefly, the ideas of the ancient Greeks who first understood astronomy formed the foundation. Atop that lies a theory of planetary motion and a theory of how all bodies move, and that was invented by Copernicus, Kepler, and Galileo. Atop that is a theory of gravity and mechanics come up with by Newton. Atop that is an understanding of electricity and magnetism, which was only made possible through an understanding of forces. Atop that is a theory of the inner nature of matter, which could have only been discovered with the help of understanding electricity and magnetism. I could continue to elaborate on the levels, but basically imagine about 50 more stories to that story, 50 more levels to this skyscraper, and what you have is this enormous pile. Now, physicists work and think at the top levels, but those top levels only have meaning if all of the earlier levels are fully understood, because it is those earlier levels that provide the proof of the later levels. And because this long chain of inference is so long and so abstract and so complicated, we now have a situation where the experts in a field are taking on faith the conclusions of those who have come before them. Now, you might say that there's nothing wrong with taking the earlier physicists on faith, so long as those earlier physicists did in fact use the scientific method and did in fact prove their conclusions. Now, in many cases, that is true. It's not true for quantum mechanics and relativity, but in many cases it is. Newton, after all, these theories at least get correct results. Our technologies work on the basis of these theories, and that's kind of all the proof anyone needs to know that they're successful, at least. But here's the problem. You can't really think and innovate in a field where you don't understand the ideas yourself. And so the final thing that has caused the stagnation in physics is that physicists do not fully understand physics, in my opinion. Not in the way that they should. Not in the way where they can really tell you all the observations and reasoning steps that allow you to understand that. Now, as a layman, of course, you don't need to understand the proof of everything, but for those who wish to innovate, for those who wish to discover new scientific principles, this kind of first-hand understanding of the proof of physical principles is going to be an enormous asset, and I would argue you can't really make significant fundamental progress without it. Now, let me briefly indicate what Inductica is going to do to implement a solution to this roadblock. The solution, in my view, is to go back to observations. We have flawed theories. We need to go back to the observations. That's what you do. We had a flawed theory of the solar system when we thought it was a geocentric theory. What did Kepler do? He made a bunch of, what did Kepler, Galileo, Copernicus do? They went back to the observations. It's no longer that simple, unfortunately. That's part of it. We have to do that, but it is insufficient. Here's why. In the modern day, the observations which constitute the evidence of these modern abstract theory, these observations are themselves the result of inference from prior theories. Inference from theories which I have already shown to be flawed. Inferences from quantum mechanics and general relativity. Going back to the observations, if we really want to do that, will require a fundamental overhaul of our entire scientific corpus, of our entire physics corpus. We will have to go back and reprove everything from the beginning. Only then will we be able to return to the observations and reasoning steps which first proved quantum mechanics and general relativity and reconsider them. Reconsider them truly with unbiased eyes. Because right now, we look at these phenomena through the lenses of prior theories, which we as physicists learned in school, and we don't really know the evidence for. We know that it's consistent with observation on some level, but we don't know how it was actually proven. And so what Inductica's mission is to reprove all of these physical principles from the beginning. My YouTube channel has already started this process of reproof by starting with cavemen counting rocks. And the reason I started so early, my intention is to go from cavemen counting rocks to all of basic math, to basic Greek astronomy, from there to reprove mechanics, from there to reprove electromagnetism, thermodynamics, quantum mechanics, etc., all the way up to quantum and relativistic phenomena, to build this perspective that will allow us to look upon quantum and relativistic phenomena with fresh eyes, without the biases of the prior theories we were already taught in college. And to aid in this process, I have written an entire theory of induction, specifically a theory of the scientific method. I think part of what's gotten us into this problem is a faulty theory of what it means to actually prove a scientific theory, and you can ask me more about that in the question period. But I've written an entire book, which is right now available on my Patreon. I've written a book. You can see an advanced copy of it. It's not published yet. You can see an advanced copy of the book, which details my theory of the scientific method. And part of what this reproof is going to do, part of starting from caveman mathematics, is to show how this theory of the scientific method can indeed be used to prove observational science with certainty. And so through that process, this process of reproving, I'm hoping that physicists of the future will be able to look at physical phenomena with completely fresh eyes and to discover the true causes of all of these wonderful phenomena that we're seeing in the physical world. So with that, thank you for your attention, and I'll open it up to questions.
Thanks, James. Appreciate that. You guys want to talk to? I don't know if the computer can you hear?
Just speak up, and I should be able to hear you.
So are there observations we're making today and conclusions we're reaching today that you believe are inaccurate as a consequence of leaning on past theory?
Yeah, so let's see. So first of all, what I'll say is that from my own perspective, the majority of cutting-edge physics is something that I am not equipped to evaluate. So for example, they recently took a photo of a black hole. Is it an actual black hole? I personally do not know. Now, this isn't to cast doubt on anything. I'm not trying to cast doubt on anything. But I'm just telling you my attitude. I don't accept a physical conclusion until I understand the observations and reasoning steps which prove it. And from my perspective, I can't speak to whether or not that's a real black hole or not. I don't have the prior knowledge required to evaluate the evidence that has been presented. Similarly, the Big Bang. I could say that I'm skeptical of the Big Bang, but it would be more accurate for me to just say I don't have the prior knowledge, even as a physicist, of how long now? Depending on how you count it, like 14 years. A physicist of, let's say, 14 years. even after all of that experience, I don't have the prior knowledge required to evaluate the claims of the Big Bang. I find it a little bit dubious because I don't think the universe can have a beginning. But was there some kind of explosion? Yeah, maybe. I'm not gonna say that it's wrong. But it's not that I'm even skeptical. It's that using my method, I would have to reprove all of the physics that was required to infer the possibility of the Big Bang before I could say one way or another. Now, there are other places where I do think, based on my current knowledge, that we've gone very, very wrong. So one example would actually be the many universes interpretation of quantum mechanics. I think many universes makes for very interesting sci-fi, but it has no evidence as a physical theory. The reason it is taken to have evidence is because in quantum mechanics, we aren't given specific outcomes as we are in Newtonian physics. In Newtonian physics, it's straightforward. A certain thing happens, and then as a result of that, another thing will happen. It's a deterministic system. In quantum mechanics, as it stands, we do not have a theory of that nature. We only have a probabilistic theory. And one way of explaining this is that all of the possibilities given in quantum mechanics actually happen, and that they happen in different branches of a multiverse. And now, that's, again, it makes for good sci-fi, but in my view, it is not enough to say that my theory is consistent with the observations. Therefore, my theory is proven. That's not how it works. First of all, any conspiracy theorist, all conspiracy theorists basically appeal to this logic. They'll point to a bunch of facts that are consistent with their claims, and then that lends plausibility to their claims. I mean, not all conspiracy theorists, because obviously it doesn't take that long to end up finding some evidence that completely goes against their claims. They can't integrate all the evidence. But here's the thing. Even if they could, that would not prove their claims. Even if all the evidence failed to contradict their claim, that would not prove what they're saying. That's not enough. And in the past, that is not the method that physicists use to prove the physical principles that our technological society stands on, that our technological society functions on. Our electrical current, our power grid system, these are based on physical principles that were proven through a fundamentally different method of science. It wasn't proven by guessing and checking. Guessing and then, oh, hey, it seems to keep being right for some reason. No, physicists didn't get lucky over and over again. So the reason why we're coming up with so many theories that really aren't proven is because we have a wrong view of what it looks like to prove something. And as I said, some examples, like one example I would definitely point to within my own breadth of knowledge would be the many universes interpretation of quantum mechanics.
I had a question.
Yeah.
So you've been talking about, there's the need to do a fundamental overhaul of physics where people are building on that tower or house of cards at a certain level, like you were saying with the electrical grid, like that foundation is stable. What is the impact if for the next 50, 100 years there is no fundamental overhaul and we keep building? Like, what actually will that impact people?
Oh, that's a good question. I don't think the impact is going to be like some kind of disaster or anything. It will just be a very sad. It will be a kind of sad state that maybe a lot of people aren't even going to notice. What's going to happen is we will miss out on all the discoveries that would have been possible. Like I said, I pointed to the first 300 years of physics, the 1600s through 1800s. This was a period of linear progression, or actually I should say, really it's been linear pretty much until 1950, 1970, something like that. The problem is from 1900 to 1950, progress was being made, but it was being made using faulty theories that undermined future progress. You could say that it was linear up until that point, and then that we're experiencing the drop off now. So what's going to happen without the overhaul? Physics is going to just kind of continue to stagnate. And what's interesting is because physicists don't even have the right view of what science is supposed to do, they don't think that science is fundamentally supposed to find underlying causes. Physicists don't even really notice the stagnation. You'll see a few physicists talking about it, but they won't really identify it very strongly. Then other physicists will say, like, well, what the hell are you talking about? We're making so much progress. And those physicists are right. We are still making a lot of progress. We're just not making it in fundamentals. When I say that physics is stagnated, I'm not saying like all technology, all applications of physics are stronger and more abundant than they've ever been because of the wealth and freedom that we now have in our modern day that's unprecedented in history. What's stagnated is something that no amount of money can buy, which is fundamental investigation into the deeper and deeper levels of these causes. That's the subtle, specific way in which it's stagnating. And we're just going to continue to miss out without some kind of fundamental overhaul to our knowledge state and to our philosophy that we use to approach physics.
My guess would be the correction between classical mechanics and quantum mechanics. So Einstein's correction to Newtonian gravitation. It's Newton's gravity could get us a certain way there, but then when we had to do more refinement, Einstein's gravitational theory was more refined to that, like GPS and things at relativistic speeds, velocities.
All of that is true, but what I would emphasize is I would not emphasize the immediate predictive power and applications of these theories. That is not what I would emphasize right off the bat. Now, that's the payoff. That's why we're doing all of this, is to have prediction and control over nature. But what makes prediction and control over nature possible? First, it's knowledge of the phenomena. And how did Einstein contribute? Well, he understood, on some level, phenomena which are deeper than the phenomena understood by Newton. He went one level deeper. Now, he explained that level in a way that was flawed, but he still went one level deeper. But now, because of those flaws in Einstein's theory and in quantum theory, we are now unable to go any deeper because of the mistakes made in the lower levels of the skyscraper. Those floors are going to need to be remodeled so that there are actual stairs to the next story instead of simply a dead end and unable to build that next story.
But it does seem to me that those lower levels in different branches of physics are constantly being broken. That is, you've got a way of viewing the world. You have observation that reinforces a theory, and then every once in a while an observation will come along and say, you know what, that theory is no longer accurate. So we looked at some of the recent observations of the James Webb Space Telescope with regard to universe. I'll use the word creation, which is a kind of a funny word, but creation. There was a model as to how stars and galaxies formed. Well, contemporary observations break that. So what do? You get a bunch of physicists who are scratching their head, new conferences, new books, a theory a day on what actually is going on. So the idea that physics has just stopped and we have to go backwards, I think you sort of have to look at the branch that you're observing. Some branches are more dynamic. Some branches are making progress at the margin, as you suggest, and perhaps there'll be a future break.
So what I'm hearing from you is the view that physics isn't always a linear progression. that sometimes it's a process of realizing that in the past you were actually wrong and that you need to fundamentally rethink your theory. Is that what I'm hearing from you?
Yeah.
That's part of what you're saying.
It's lumpy. Progress is more lumpy. You make it marginal. Something profound happens.
Yeah, that's certainly true. But what I'm specifically asking is are you saying that it's not linear, that sometimes you have to go back and realize in order to come to new theories, you have to throw out old theories? Is that part of what you're saying?
I'm saying that a new observation that is not consistent with theory will break that.
Yeah. Now, I disagree. I actually disagree with that commonly held perspective about science. I think science, when properly conducted, is a linear, cumulative process. Now, it does come in lumps, like you said. There's certain times when some new insight happens, and then, so I guess I shouldn't say linear, but it is a cumulative process. So an oft-cited example of science being non-cumulative is a citation of Einstein's theories as overruling Newton's theories. Newton had a mechanics, he had a theory of gravity, and what we find with Einstein's theories is that when an object moves nearly the speed of light, or when an object is in a strong gravitational field, we find that Newton's laws are not exactly correct. Okay, and so as a result, what people often say is we had to throw Newton away and accept Einstein instead. That is not, in my view, an accurate portrayal of what's going on. So first of all, it's worth noting that the only way Einstein discovered the things that he discovered was by using Newton's theories. Okay. Now, second of all, it's true that the laws of gravitation and motion were refined, were altered by Einstein's discoveries, and really it was Lorentz's discoveries to a great extent. Einstein kind of gets too much credit. Einstein deserves some credit, but like Lorentz deserves a lot of credit too. It's worth noting, so I should mention his name just out of justice. So, once Einstein and Lorentz discovered these additional factors, that doesn't invalidate the factors which were discovered by Newton. It's simply additional factors. It's simply additional cause and effect relationships which apply to matter in motion and to matter inside of a gravitational field. When someone discovered zebras, we didn't say, oh, horses are wrong or horses have been overruled. It's just no. And like obviously when you put it that way, it's like, okay, obviously that's just a different animal. And, the discoverer of horses, that was horses are real still, and then zebras are just this new thing also. That's the way we should think about it, is that simply new cause and effect relationships were discovered by these new scientists. The old cause and effect relationships discovered by Newton are still completely valid. We need to think of it that way, otherwise we're blowing up our foundation each time as we try to progress. But like Einstein relies on Newton as part of his foundation. So I think science should be thought of as cumulative when done properly. Sometimes science is not done properly, like in the case of special relativity, general relativity, and quantum mechanics. And those theories will have to be altered. Those floors will have to be remodeled, essentially. It's not that they're completely wrong and just need to be blown up, but they will need to be significantly remodeled. That is, and to continue that cumulative progression.
Does anybody online have a question to Ben or Gary?
Can you all hear me?
Yeah.
Yes.
I have a question. I don't have a physics background, but I have a math degree. Well, so just generically, where does very advanced math that doesn't have like a physical equivalent, come into play in the future of physics?
Good question. Let's see. In my, you may have heard. I don't think you were here for this part, but I'll repeat it just in case you weren't. I made the claim earlier that math is a empirical science, just like physics is, in my view. I do believe math has certain aspects which are drastically different from physics, yes, but being non-observational is not one of the features of mathematics in my view. As a result of this, I believe that proper math, must be motivated by observation. It must be an answer to some question that arises in reality. Now, that doesn't have to be a physical reality. That could be a reality of, it could be some facts about biology. It could be some facts about sociology. It can be some facts about finance. We're trying to figure out how much someone owes on a loan. We're trying to figure out what is proper to compensate the loaner for his time away from his money. All of these are mathematical problems that people observed. They observed that they were loaning money, so to speak, and they thought, well, how do I calculate this in a way that's fair to me as the loaner and fair to the debtor? What kind of interest would be justified based on the fact that I'm giving this person a value. I'm letting them use my money for a certain amount of time, and I'd like to be paid for that. I'd like to be paid for that value that I've given away. So it doesn't have to be physical, but math to be valid, in my view, requires some kind of observation of some real phenomena. And I don't follow modern math too much, but from what I understand, mathematicians basically see math as a free creation of the human mind. I've heard mathematicians describe their field as similar to art, and I repudiate that. Math that has no application to reality is an abomination. It's not art. It's like a Pollock painting. It's a disgrace. It is a repudiation of its purpose. Just as, for those of you who may not have heard it, like Pollock paintings are these paintings with like splatters all over them. That's a repudiation of beauty. It's a repudiation of the purpose of art. So, and in like form, I think calling mathematics art is a repudiation of the true purpose of mathematics, which is to identify quantitative relationships in the real world and come to conclusions about those relationships. And calling it art turns math into a stupid, useless game. So that's my uncontroversial opinion on all of that.
Well, there are other views.
Yes. Yes. I'm aware there's other views. And please do challenge me on any of these because I welcome the opportunity to explain myself further.
Well, I think the categorize as abominations is a little rich. By that logic, we might categorize all of art as being an abomination.
Well, no, I mean, there's plenty of art that's real art, like, take any legitimate piece of art, say, any movie that really inspires you, any song that really makes you feel deep emotions, any painting like, painting or statue. My favorite sculpture is Bernini's David. So like the guy who's about to throw a rock with his sling, and his face captures this incredible focus and concentration on a goal. Like that really inspires us. Whereas like splattering paint, that has no meaning. That has no meaning whatsoever. It's a repudiation of the purpose of art. And in like form, I think mathematics, which is just form without function, rules for no reason, rules that you just follow, and oh, hey, neato, I added a bunch of columns of numbers. Like, well, what do they mean? Well, I don't know what it means, but it's just, isn't it beautiful? No, it's not beautiful. It's useless. You've done something that is a waste of everyone's time, most especially yours, and you should respect yourself more than to, spend your time doing something that has no purpose. So yeah. I mean, I feel strongly about this because mathematics, it's something I've dedicated my life to. If I were an artist, I would have a lot more vitriol for someone like Pollock. I'm not an artist. I'm a physicist.
Yeah. An artist. If you were an artist, for you to say that if you were an artist, a true artist, that you would hold a vitriol for Pollock, it seems an extraordinarily subjective position that you take to be objectively true. And with regard to your observations related to math, to call it something an abomination and a waste of time for folks that find beauty in it where you do not, I think that's a little out of bounds.
I see what you're saying, but I think these claims can be evaluated objectively. So with regard to Pollock, yeah.
I was just going to say, I think the beauty of art is that it is so subjective, where we all find meaning in different ways of expression. And just like with science and music, since some people really get that joy out of discovery and saying, what happens if I put this number there, or put this, I'm not a math person, this letter there, versus other people really get joy out of the practical application in terms of what is the impact of my work. I was really curious, like Gary, you said your background is in math, so what is like your take on the future of advanced math and physics? Gary, you're on mute if you're speaking.
I wasn't speaking, sorry.
Did you hear the question? I'm sorry, Wendy asked.
Sorry, I had some background noise, that's why I had to mute myself. What was the question again? Sorry.
I was just curious on your thoughts to your question about the future of mathematics, advanced mathematics.
Well, I mean, my only follow-up, I guess, is that some things can be so advanced that we don't understand the physical equivalent yet. That's my only back to that.
Yeah, there's a common view that mathematicians can go out on their own whimsy and freely invent like these new systems of rules that are basically arbitrary and have no evidence, and then later we find that these arbitrary musings ended up having applications to physics later. I would have to study, so I have to be honest with what I know and what I don't know. I would have to study the history in order to really make this claim, but I find it highly unlikely that that has ever happened. I find it much more likely that these things have been invented and then like theories of modeling were like kind of used after the fact, but they weren't actually used to describe the true cause and effect relationships. To think otherwise would be to hold the view that somehow these mathematicians got wildly lucky in their arbitrary, unmotivated musings about how to combine numbers together, somehow ended up describing reality. That sounds very unlikely to me.
I think the only example I might have is cryptography was for years advanced mathematics that then finally had an application that was worthy and useful.
Interesting. Yeah, I should think about that as an example because, like, in an application like that, like the complexity itself is the thing that has application. Are you thinking primarily of number theory, kind of like applications in number theory? I'm sorry, like random musings, as I would call them, in number theory, ending up having application to cryptography? Is that the example you're thinking of?
Well, I'm a computer scientist and programming for years and just been around systems. So programming often uses a lot of techniques in math, and you come up with new things, and what you come out with, something like cryptography, you're using techniques from that are out there, that are common, that are published, that are built upon tool sets after tool sets after tool sets. I'm just thinking about it from that way. I'm very far removed from any advanced math. It's been 40 years since I've been in school, so that I'm not really that up on. I mean, number theory when I took it was, I don't remember much of it, but just in general, something like cryptography being very complex, and I know it's there wasn't a lot of use cases for it for many years until software development came along.
Yeah. Now something I'll add to this is it's worth noting that all of these cryptographic concepts and rules, they probably were invented with a real application in mind. These, this is not arbitrary musing. Like, cryptography as a science has been around for at least hundreds of years, if not thousands, if not, maybe a couple thousand. So, like, these methods, they're not arbitrary. They come from people really trying to actually encode messages. And maybe you can use these tools towards new applications, but, like, that doesn't mean that. And then now here's another thing to think about, finally. Let's say you did come up with a couple examples of random musings ending up being useful later. Wouldn't it be more productive to only focus our energies towards those projects which are known to have application? So it's not that you can't do something useful through random musing. It's that you're much more likely to do something useful if you are disciplined and you don't just follow your intellectual whimsies, but rather you identify why you find something interesting and justify that feeling of interest. Justify that feeling of interest, saying, like, okay, well, this is interesting because it can lead to this positive outcome. So I think science and math would be better suited by that kind of motivation rather than, it just interests me. I feel this, and why? I don't know, I haven't really thought about it. It gives me good feelings. That's not good enough. We shouldn't make our decisions in life based on pure feelings.
You're suggesting that mathematical innovations should not be pursued unless there's utility as a goal?
No, not necessarily utility, because you can definitely make a case for simply identifying fundamental mathematical relationships as an end in itself, because fundamental mathematical relationships, just like fundamental laws of physics, have application. So what would be an example of some kind of fundamental law? So let's imagine that a number of imagine a time in, like, let's say the ancient Arabic civilization during the Islamic Golden Age. They were the inventors of algebra. Let's say that, you have some Arabic mathematician and he's written down a few algebraic equations, a few of them, right? And he's kind of guessed and checked his way into figuring out how to solve those algebraic equations, okay? And then he says, hey, wouldn't it be great if we had some kind of algorithm, some kind of systematic way to solve all algebraic equations, some kind of systematic method? And then he comes up with that rule: what you do to one side, you do to the other. Which, by the way, in Arabic, that's al-jabar, which apparently means the reunion of broken parts. That's their way of saying what you do to one side. I don't know why they called it that, the reunion of broken parts. I don't know. Whoever that guy was, he was thinking about it a certain way. And so what you do to one side, you do to the other. It's called al-jabar. That's how we got algebra. That's how we got our word for it. That would have been completely justified because it had already been identified that these algebraic equations were of interest. And he doesn't necessarily have to justify the general rule by some kind of immediate application. It's enough to just say, hey, these algebraic equations can be written down. Is there a way to solve all of them in general with one algorithm? And that would be justified in the same way that investigations into the underlying causes of planetary motion would be justified. Newton probably couldn't think of some immediate application, but knowing the laws of physics are powerful, and you don't need to justify it with some application immediately. You just know, if we know how this thing works, then that will give us power in the future. We'll figure out some way to use it. My point is that you at least need an argument of that sort to justify the effort, and to justify it, number one, to yourself, because otherwise you're wasting your own life. Like, it's on some level, like, I'm mad at mathematicians for making a mockery of one of my fields, but like, really, the number one person they're hurting is themselves by going down these flights of fancy without really checking why this is important or why anyone would care.
So these folks that are wasting their lives, as you say, is it possible that they're not? Is it possible that in the end of their days they can look back on their work and see something of merit on its own merits without having utility? And to go further, isn't it possible that those folks that knew of Kepler's work would say that this indeed is a flight of fancy and it has no use?
Well, I mean, I think Kepler's work under my standards clearly had a use. He was identifying, the causes of planetary motion and the nature of planetary motion, which, again, these are fundamental facts about the universe, and fundamental facts are powerful. But to address someone who at the end of their life to address the issue of, like, at the end of their life, would someone maybe find satisfaction? I mean, I don't know, like, people can lie to themselves during their lives, at the end of their lives, whatever. They can put themselves under whatever delusion they want. That doesn't change the facts of the matter, that they did something.
So it's so delusional for someone to say at the end of their life that they look back on what they regard as being beautiful and being somehow self-delusional? Is that your point?
I mean, I think it follows from an incorrect understanding of beauty, is what I would say.
You must have some sort of privileged view on what constitutes reality and the purpose of life, and that's a lecture for another day. But,
I mean, yeah, I think there's a right and a wrong way to live your life. I think certain ways of living your life will lead to suffering, and other ways of living your life will lead to happiness. And the ways that lead to happiness are correct, and the ways that lead to suffering are incorrect. So
he looks back. I don't think he would say anything with regard to suffering. He may in fact say, this was beautiful. Some may, some not. But that's really their determination.
Yeah, it's of course his determination, because, like, he's the one it matters for. But I would just say, like, hey, I would tell him during the course of his life, I would tell him, hey, like, wouldn't you be more fulfilled if you chose pursuits that were productive instead of simply kind of thinking about things that don't relate to reality? I would offer that to him in the spirit of just helping him live a better life.
This is a good discussion. I'm having like a mental image of all of science as like a courtroom. Everyone goes up and presents their business case to James, and it's like valuable. No.
Well, I mean, at the end of the day, it doesn't really matter what I think. What matters is what's true and what's false. Like, does this help your life or does it not help your life? I have a certain judgment about what helps your life or doesn't. And, I'm kind of sharing that. But, like, the reality, the courtroom, the judge isn't me. The judge is reality. Will you, live a life that is, full of more fulfillment or less fulfillment? I guess suffering isn't really on the table here as an option. We're just talking about how someone pursues mathematics. But, like, if someone pursues things that are related to reality, then they're likely to find much more fulfillment than if it's unrelated to reality.
Perhaps.
Yeah, I think it'd be cool to have like that jury of peers where you're coming from different disciplines and where everyone has different takes. So I think, James, yours was really interesting to learn about, like, that cross-collaboration of ideas, especially where there is discord. I think really fosters innovation. Most people make those discoveries and make things.
I think that's why you have business people and marketing people in conferences, because they take the ideas that may not be useful or by themselves useful. You get them more practical use cases and tested in the real world. You get the collaboration among scientists and businesses can surface things that may not necessarily be useful, but inspire someone to do something that is effectively useful or marketable.
Yeah, I think there's often a lot of steps that have to be made in addition to, fundamental principles to get those principles actually delivered to a customer towards some productive end. There's a lot of steps between the discovery of electromagnetic induction and our power grid. There's a lot of steps between those, and you need a lot of thinkers at every level of that process to actually deliver it to people and make a difference.
Yeah.
I just have one comment. Just for me, studying science and engineering the past couple decades, especially I'm in the medical device industry, I've come across through using technology to help or improve people's lives and at least give back to the community. I don't necessarily wouldn't think of it as art, but I guess you could. I do take some creative steps in the design of a medical device that I've been developing for years. So my day-to-day experience, I kind of use that not just on medical devices, but I've been in multiple industries, with aerospace, semiconductors, photography, and I work on cars, and I kind of incorporated all of my experiences into a device that will help people save people's lives in the future. So,
something I want to address for many of you, since many of you here have a general interest in science. It's not necessarily going to be your career. You're not trying to use science towards some productive end. Let me address your particular case as it fits into my view on this. Is learning generally about the way the world works is of value. It adds an aesthetic. Aspect to your experience of the world, to understand how it all works. It also has practical applications in that it disciplines your mind into understanding on deeper and deeper levels, like how to apply laws and definite rules to things, and understanding that everything does have a cause and how we use that cause towards some sort of beneficial effect. So I think maybe what some of you are recoiling against is the idea that if we really thought about science the way that I think about it, then your amateur pursuits of science and your interest in that would be invalidated. And that's absolutely not the case. What I'm saying is that you should because it is very practical, it does serve your life. What I'm saying is I want to focus on the positive here, and I've kind of come off as a little bit too negative because I kind of got triggered by a bunch of things that kind of make me mad. But let me emphasize the positive, productive aspect of what I'm trying to say here. As you pursue your personal interests in science, take the time to think about how to pursue that interest in a way that most benefits your life. And just because you feel like doing something doesn't necessarily make it the best path towards fulfillment, basically. Think about what sorts of things really deliver the most to you when you ask that question, what is it that this knowledge really brings to my life? And if you think creatively in that way, you're going to find answers that are special to you that allow you to go deeper than you would have if you just kind of, I'll just surf YouTube and just kind of look at whatever, seems good to me right now, or whatever it is. If you have a more conscious, mindful process of selection, you'll enjoy your hobby much more.